To finish up this section, we're going to look at some properties of definite integrals. We're going to go over them kind of quickly. First property is that if we've got the integral from a to b of this function f of x, then we can change the limits of integration and go from b to a, but it changes the sign of the definite integral. So if a happened to be larger than b, and we liked the smaller one on the bottom and the bigger one on the top, we could switch the order, but we have to make the integral negative. The next one says that if we try to find the integral of f from a to a, well, then there is 0 area, because you can imagine from a to a, the delta x would have to be 0. So if the base is 0, it doesn't matter what the height is there, the integral is 0. Next, if we take the integral of a constant from a to b, then we get c times b minus a. And to see that, here's our constant c. We're going from a to b. So what we have is a horizontal line from a to b, like so. We saw this example just a minute ago. This is just area of a rectangle. The base is b minus a, and the height is c. So that's just area of a rectangle. Next one says that the integral of the sum is the sum of the integrals. That is, we could split the integral up if there's addition, and number 4 is the same thing except for subtraction. So we can split that up with addition or subtraction. And then number 3 says that if we have a constant times a function of x, we can factor the constant out. These all go back to the limit of the sum definition, because if you can think about 2, 3, and 4, if you're thinking about the integral, the definite integral, as a limit of a sum, you can split up a sum of a plus b is the sum of the a's plus the sum of the b's. We saw that when we were talking about the summation rules. And then if you think of this one as this number 3 as the limit of the sum, again, if you have a constant factor of c, we can factor that constant out. So let's look at an example to use some properties to find this definite integral. So we did a problem, x squared from 0 to 2, and we found it was 8/3. So that's all we know about this one. So what I'm going to do is I'm going to use number 2, property number 2 first, and I guess this is probably number 4. Split it up into 2 integrals, like so. Then I'm going to use property number 3 to factor out that 2. So from 0 to 2 of 4 dx minus 2 times the integral from 0 to 2 of x squared dx. So now I'll use property number 1, which says, hey, that first integral is just area of a rectangle, so it's going to be c times b minus a, then minus 2 times, we know the integral of x squared dx from 0 to 2 is 8/3, so it's just going to be 8 minus 16/3, whatever that works out to. Let's work that out. 8 minus 16/3 is 8/3. And that's our solution. Next, we have property number 5, which says that if we've got the integral of f of x from a to b, we could split it up and stop at c along the way. So here's our integral. Here's a, here's b, and here's c. So the integral from here to there is the same as the integral from a to c, and then plus c to b. That's what that says. We can split the integral up into pieces and stop in the middle, like that. Next, we have a couple comparisons of what's larger. The first one says that if we're dealing with a positive function, from a to b, then the integral should be a positive number. That makes sense because if we think about a positive function, the net area of a positive function, well, that should stay positive because all of the heights are positive. The next one says that if we have f of x bigger than or equal to g of x, so here's f of x and here's g of x, from a to b, then the definite integral of f of x, in yellow, is larger than the definite integral of g of x. So again, if we're thinking about this in terms of areas, the area of the one that's further up, larger, the larger function, is going to be larger than the area of the smaller function. Number 8 says that if f of x is between m and m, so let's say here's little m, here's big M. If f of x is between those two m's, let's just go like that, from a to b, let's call that a and that b, then the definite integral of the f of x is between these two. So what that's saying is if you have this big rectangle, that big rectangle area is m, big M, times b minus a. You've got this green rectangle. That green rectangle area is small m times b minus a. So if we're thinking about this in terms of area, the area under the curve, let's say that this is the area under the curve. The area under the curve is going to be smaller than the area under the big rectangle, but larger than the area under the small rectangle. And that is the end of our properties. We won't have to prove them, but they do come in handy when trying to evaluate integrals occasionally.